Now, this becomes a lot more difficult if we do things in 2 dimensions. Now, because motion or other types of vectors can occur in 2 dimensions, it doesn't always occur in 1 dimension, right? Superman doesn't always fly in a straight line. Sometimes he flies in a straight line and then he flies at an angle. Okay? The value will no longer just be the sum of the values of the vectors. The value will always be somewhat less than the sum of the vectors. And let me just remind you, if I have 10 somethings and I have 5 somethings, those are going, if they're in the same dimension, they're going to add together to give me 15. But if I have 10 somethings and 5 somethings here, that value at an angle there is never going to be 15, right? The only way that it's going to be 15 is if the 10 and the 5 are in the same direction. But if the 10 and the 5 are in angled directions compared to each other, the result is always going to be less than 15. Okay? The result will always be somewhat less than the sum of the vectors. Now, we can represent these vector additions graphically on 2-dimensional coordinate systems in a manner similar to that of 1-dimensional analyses. And our rules are going to be the same. Most of our rules are going to be the same. All added vectors must be labeled with the type of vector and the magnitude. And you're going to add the values to the added vector labels below, down here. So I have a vector diagram where I've got a motion in one direction and then a motion in the other direction. And then there's my result. Notice I'm saying that it's still the sum of 2 vectors, right? D equals D1 plus D2, or D resultant equals D1 plus D2. Now, I'm not going to find that sum by adding those numbers together. This just says I'm adding this vector to this vector. And what's the value for D1? According to the graph, 10 kilometers. Okay, and the value for the other vector is? It's going to be 5 kilometers, right? Okay, so I want you to show me a label and a value for all the vectors. That's one of our rules. Okay? The resultant vector should be labeled and a formula indicating the sum should be displayed on the diagram. However, the process of finding the sum will be more complicated and should be illustrated off to the side of the diagram in the workspace. Okay? Now, it's been a while since I've actually written these notes. I don't actually want you to put that there anymore. As far as the resultant vector, if I'm trying to find the resultant vector, I only want you to just put question mark. Okay? Whichever side we're trying to find, I want you to put question mark for. So, a formula indicating the sum should not be displayed on the diagram. Sorry. Again, I promise this isn't COVID, it's just allergies. I didn't mean for you to have to see snot dripping out my nose, though. Scroll. Why won't you scroll? No, it went too far. This is a brand new computer. It should be able to handle all of this. Okay, so formulas and calculations should be shown if added vectors are at right angles. The resultant value can be found using Pythagorean Theorem, and the angle indicating the direction of the resultant can be found using the inverse tangent of the opposite over the adjacent sides, and we'll illustrate that here. So this will become our strategy for this kind of problem. And in general, we will not do anything other than two-dimensional motion that's at a right angle to each other as far as vectors go. So let's look at this is maddening. One other thing that you should be aware of, and we talked about this when we talked about trig functions, the resultant could also be determined using a ruler and a protractor if we drew these things to scale. And I want you to be aware that there are two different ways that we can draw our vector diagrams. We're going to use the tip-to-tail method because the parallelogram method's a lot more prone to mistakes. So if I have a vector in this direction, and let's say it's a velocity of 10 meters per second, and then I have a vector, a wind vector in this direction, let's say its velocity is 5 meters per second, so that's velocity 1, that's velocity 2, and that's 5 meters per second. Then this is the tip-to-tail method of drawing the vector diagram. Technically, because the velocity affects the object at this point right here, this is where the object is, okay? It's got a velocity of 10 meters per second in that direction, and the wind is blowing at 5 meters per second on it here. Technically, we should write these vectors like this. Okay, technically we should write them like this. But that doesn't show these two vectors being added together, right? That just says, hey, both of these are affecting the same object. Both of these vectors are affecting the same object, but it doesn't do much to help us visualize how we can add these two things together. Okay, so what I'm doing is I'm moving this vector right here over here to the tip. This is the tip-to-tail method. And that way you can see what the result looks like. Okay, that way you can see what the result looks like. If I tried to do that with this, okay, my result's in the wrong direction there. Do I go this way or do I go that way with the result? And in fact, it's in the wrong direction, right? So that's not how I want to do things because it's more confusing. Okay, so this is the tip-to-tail method, but if we wanted to, we could do this. Two vectors drawn from a common origin and used to construct a parallelogram. And what I mean by that is we draw straight lines that are perpendicular to the tips of each vector. And you can see that they're going to intersect where my resultant should be. Okay, so this is the parallelogram method. Okay, do not draw the resultant between the two tips of the vectors. That's wrong. Draw a line that's perpendicular to this, draw a line that's perpendicular to this, and they'll intersect, and where they intersect is where your resultant is. We won't use this method because it's a lot more confusing. Okay, although it does accurately show that both of these vectors affect the object at the origin there, rather than having to move this vector to the other point. Okay, the order of addition doesn't matter. So now, a descent vehicle.
Yeah.
Landing on Mars has a vertical velocity towards the surface of Mars of 5.5 meters per second and a horizontal velocity of 3.5 meters per second. Okay, so it's coming down at 5.5 meters per second, but it's not coming straight down. It's coming down at an angle. So we could also say the horizontal velocity is at 3.5 meters per second. At what speed does the vehicle move along its descent path, and what angle with the vertical is it? So according to my problem, I'm descending at 5 meters per second. I'm going to call that velocity 1 at 5.5 meters per second. Okay, and I've got a horizontal velocity, V2, of 3.5 meters per second. Okay, is this how you read that? Would you?
It's excused.
Okay, but you still missed a whole bunch of crap.
It's still excused.
Okay, so sure. Okay. So, at what speed does the vehicle move along its descent path, and at what angle vertical is it? So, my result is always going to be from the beginning of that path to the end of that path. Okay? And I know how to find that. We're going to label this V. And in order to find V, now I can create a formula. Since this is a two-dimensional thing, I've got a right triangle, and I'm going to solve this using the Pythagorean Theorem. I'm going to write out my formula here. V equals the square root of V1 squared plus V2 squared equals the square root of 5.5 meters per second squared plus 3.5 meters per second squared. I get 6.52 meters per second. Okay, So its actual velocity is 6.5 meters, 6.52 meters per second. So the point then is that maybe the way that their systems work, their systems on this rocket work, is that I can tell how fast I'm descending, and I can tell how fast I'm moving with reference to the ground, okay? So if I'm going in this direction, my ship can tell, hey, I'm descending at 5.5 meters per second, and I also have a ground speed of 3.5 meters per second, but that doesn't tell me how fast I'm actually descending along my descent path. I have to do this to figure that out, okay? And so the speed along this path will literally be the length of that vector, okay? The speed along that path will literally be the length of that vector, okay? And now we also want to find the angle with the vertical. We're going to call that angle theta. And in most of these situations, we will have the opposite side and the adjacent side. There may be situations where we actually have one of the sides in the hypotenuse, but most often we'll have the opposite side and the adjacent side of this triangle. So I can also figure out what the angle here is by using the inverse tangent, okay? If it was the opposite side in the hypotenuse, I would use the inverse sine because sine is OH, right? If it was the adjacent side in the hypotenuse, I would use the inverse cosine, but I'm going to use the inverse tangent here. So I know, and this will be something you don't have to write out, you know that tangent equals opposite over adjacent. And so you know that the angle equals the inverse tangent of the opposite over the adjacent. If you know this already and it's firmly in your brain, don't worry about writing this down, but this always helps me. I know that the tangent of this is the opposite over the adjacent, but wait a minute, I don't want the tangent, I want the actual angle. So the actual angle equals the reverse of this process, or the inverse of this process, the inverse tangent of the opposite over the adjacent, which equals the inverse tangent of 3.5 over 5.5. And since this is just a ratio, I don't need to put my units in. And remember, second tangent, and then 3.5 divided by 5.5. I get an angle of 32.5. Is that what you got?
Yes.
So my angle is 32.5 degrees. Okay, this is how we'll do most of these problems. So the Pythagorean theorem and the inverse tangent will become your friends in this type of a scenario. Okay, Trayton, I need you to take your hat off. Any questions about that scenario? Recognize that was a scenario where I was given two things that were added together, right? And just because they're added together at an angle doesn't mean they're not added together. They were added together, and I was trying to find the result. Okay? If I'm trying to find one of the added values, we remember we have to do it a little bit differently, right? If I'm trying to find one of the added values, we have to do this a little bit differently. The ship leaves its home port, expecting to travel to a port 500 kilometers due south. Before it even moves 1 kilometer, a severe storm blows it 100 kilometers due east. how far is the ship from its destination, and in what direction must it travel to reach its destination. Okay? Now, you have to be able to read this problem and know that expecting to travel to a port 500 kilometers due south is the final value. That's my answer. That's my resultant. That's where I'm supposed to end up. Okay? So that's the final value. And I have been given one of the things that I am to add together to get to that 500 kilometers. Okay, so I'm going to write that my final displacement D equals 500 kilometers. My final displacement D. I don't need a subscript because that's my final thing. Now remember, in the one-dimensional things, when we had a final value, or we had a value to add and the final value, they started at the same point, right? It's going to be the same thing here. If I've got a final value and then I've got one of the values to add together, they're both going to start at the same point. And I'm going to be moved 100 kilometers. Who's that?
Some person.
He said, is this the wrong class? And I said, definitely not that.
I didn't hear you say that.
It was weird. Not a fan.
Okay. Anyway, this is the value that I'm starting with, and this is where I'm ending up. So the question that I ask is, what do I have to add to this to get me to my final spot? What do I have to add to this to get me to here? And it's just like with the one-dimensional thing. I just draw a vector from where the first one ends to where the total ends. And this is the vector that is going to be D2. Okay? I don't know what it is yet, but that's what it's asking me. I am expecting to go 500 kilometers due south, but I'm blown off course 100 kilometers due east first, and then I need to figure out what D2 is. Now, this is the hypotenuse, so I can once again use the Pythagorean Theorem to figure that out. D2 is going to equal the square root of D squared plus D1 squared equals the square root of 500 squared plus 100 squared. I think it's like 609.
It's 509.
Or 509. 509, that's it. Oh, is it? What, 509 point?
It's 509.90195.
Okay. Erase the other one. So 510 kilometers. Okay. Now I want to know what direction I need to go in. Okay. I want to know what direction I need to go in. And I want to know what direction with reference. It doesn't matter what my reference is here. I'm going to choose my reference as the east line here. I want to know what the angle is with reference to going west. How far south of west do I have to go? How far south of west do I have to go? And if I use this as my reference angle here, this is going to be the opposite side, and this is going to be the adjacent side. So once again, I can use my inverse tangent to figure this out. And you could ask, well, why don't I use this as the hypotenuse and use either the sine or the cosine? Generally, we don't want to use calculated values. This is a calculated value. We figured it out. It's actually 509.9 something, and we rounded it to this number, so we don't really want to use that number. We usually want to use given numbers when we can. But I know that I've got the opposite and the adjacent side, so I can say tangent of theta equals opposite over adjacent. Then I can say theta equals tangent inverse of opposite over adjacent, which equals tangent to the -1 of 500 kilometers over 100 kilometers. Again, it's a ratio, so I don't need units. So I'm going to go second tangent 500 divided by 100. I get 78.7 degrees. And we're going to say south of west. Okay? This is the west direction. This is the south direction. Okay? So that is south of west. We can't use the word southwest here because southwest implies exactly 45 degrees. Okay? So again, this angle here is 78.3 or 78.7 degrees south of west. Any questions about that? For both of the one-dimensional and the two-dimensional, we did one problem each where we had the addition of two things to get the final, and then we did one problem each where we had the final and one of the things that we were adding, and we had to find the other thing that was being added. Okay, if you remember how that works, that will be really helpful to you. Okay, we want to just start for a couple of minutes. We're not going to go a whole long way into it. We want to start by talking about something called components of vectors. Okay, and then we'll stop. Any vector can be represented by the vector sum of two or more components. That is, we can break any vector into its component vectors. So here's what I want to show. If I have this vector, I could break that into two other vectors. I could say that's the vector sum of this plus this. Would you not agree that if I add this to this, I end up getting to the same place? Okay? Or to get this vector, I could add this vector and this vector. So I could represent this vector by adding these two vectors together. Or I could add these two vectors together to give me this vector. Okay? How many possible sets of vectors could I have to add together to get any one of these vectors? Yes. This isn't the only set of vectors that I could add together to get those vectors, right? Would you not agree that I could have an infinite number of vectors that I could add together to get this vector. I could go like this. I could go like this. I could go like this. Okay, so there would be an infinite number of pairs of vectors that I could add to get to that vector. These are called components. Okay, but we only want to do this in a special way. We only want one of those infinite numbers of pairs to be used. Okay, if I have this vector, I want to break that into a horizontal component, and let's say that this is a velocity vector. I want to break this into a horizontal component and a vertical component. Or I would also call this a component in the x direction. I could call this a component in the y direction. Okay, so I could say that this is the horizontal component or the x component. I can say this is the vertical component or the y component. Okay, we can find the lengths of these components by finding the product of the parent vector and the appropriate trig function. Remember, cosine equals adjacent over hypotenuse, and sine equals opposite over hypotenuse. So, if I have this vector, and I want to find this side of it, let's say this angle is 30 degrees, and I want to find Vx, okay, I want to find Vx. Remember, this would be the hypotenuse, and this would be the adjacent side. Let's put some numbers to this. Let's say that Vx, or V equals 100 meters per second. And you can see that the horizontal velocity, or the ground speed of this particular thing, would not be that full 100 meters per second, right? I'm going 100 meters per second this way, but I want to know how fast I'm going with reference to the ground. And I know that this is the adjacent side and this is the hypotenuse. Okay? And we can remind ourselves that we have this strategy. When I'm trying to find the length of a side and I've got another side and an angle, we had this strategy. We said, label these things first and then say, what side do I have? I have the hypotenuse. What side do I want? I want the adjacent side. Therefore, I have to use cosine to find this. And cosine of theta equals adjacent over hypotenuse. Well, guess what? It also equals Vx over V. Okay? And I want Vx. So I can isolate Vx. I can multiply both sides of the equation by V, and that's going to give me Vx equals V times the cosine of theta. Well, I've got those values, right? I've got 100 degrees here, 100 meters per second, and I've got the cosine of 30 degrees. I think that would equal 86.7.
Quick.
It's what?
I got 86.6.
Repeating?
No, 86.60.
Okay. Okay, so 86.6, we'll go with that. Okay, meters per second. Okay, 86.6 meters per second. So I can find that using the cosine. Recognize that the length of the component of the vector that represents the opposite side can be found using the sine. Again, I've got v equals 100 meters per second here. And now I want this side. I want vy. And it's the opposite side, right? And I've got the hypotenuse and I want the opposite side. So I can say then that I need to use the sine, and I know that the sine of theta equals opposite over hypotenuse, but oh, by the way, it equals vy over v, and I want vy, so I can multiply both sides of this equation by v, and I can get vy equals v times the sine of theta equals 100 meters per second times the sine of 30 degrees. And you should all be aware that the sine of 30 degrees is 1/2. So this will be 50 meters per second. Okay? So that's going to be how we solve these things. And then recognize that the angle can be found using the inverse tangent of the opposite over the adjacent side. But we already know what the angle is, or we wouldn't have been able to find the other thing. But just in case, I've got 100. And now I've got Vx equals 86.6. And I've got Vy equals 50. So if I want, I could find that tangent of theta equals opposite over adjacent, and theta equals the inverse tangent of opposite over adjacent equals the inverse tangent of 50, not 500, 50 over 86.6. And that should give us 30 degrees. Is that what you got?
Mm-hmm.
Okay, good. Equals 30 degrees. Okay, so when we start next time, we'll talk about how we're going to use components in these problems. Okay? Any questions about the math that we've done today? It's just an extension of what you've already learned in trig for most of you. And it's pretty straightforward if you follow a strategy.
Do you want us to keep these or turn them in?
I'm going to ask you to turn